It's a super duper pleasure to have this colloquium today. Neutron stars, I would say, are the gift that never gift giving, quit giving. And it should be interesting to the whole audience, including condensed matter physicists, because it uses such a variety of physics and astrophysics. And Gordon Baym, our distinguished speaker, has been really involved in it almost from the very beginning. He pointed out to me that his first visit to the Aspen Center for Physics was in the summer of 1967, and he's come almost every year since. The pulsars were discovered, neutron stars were first much earlier. I'm going to skip the history because he'll talk about it. Pulsars were discovered in December before his first visit to Aspen. He's got a super distinguished career. He was a student of Julian Schwinger. He's professor at emeritus now at University of Illinois. He has worked on condensed matter physics, nuclear physics, AMO, neutron stars. He was elected into the National Academy when he's 47. He's received the Beta Prize and the Onsager Prize and the APS Medal, which is only a few years old. I think he was maybe the fifth or fourth person that got it. And it's really to the very, very most productive and distinguished physicists. So it's a very great pleasure to have you.
Okay. Neutron stars are very tiny. They're about 14 miles or so in diameter. And when we're sitting over Aspen, stretch roughly to Woody Creek from here. What you see in this other picture here is how we see them as pulsars. They emit electromagnetic radiation, they rotate, and as they rotate around, the passes you see a flash. Oh. Okay, good. Okay. This is a cross-section of a neutron star. They range in masses from the water. Let's work. They range in mass of water a little over the mass of the sun to a little over twice the mass of the sun. Radii about 12 to 13 kilometers. Temperatures inside range from 10 to 6, 10 to 9th Kelvin. 10 to 9th Kelvin, for those of you who do is high energy, it's like 100 kilovolts. But they're just basically giant nuclei with a baryon number of 10 to the 57. And kind of magnetic fields all over the place, including huge magnetic fields, 10 to the 16 Gauss. The gravity is exceedingly strong. Surface gravity would be in the order of 10 to the 11 times that on Earth. So the sensing, you drop something, it falls at a certain rate. A neutron star would fall 10 to the 11 times faster. Here. Okay, that means the binding energy of particles at the surface is in order 10 to their rest mass. This is a rough picture of a neutron star. Solid. Here's a mountain. Does anybody recognize a mountain? The mountains can be about almost a millimeter high. They're higher than that. The gravity is so strong, just pulls all the stuff down. Collapses it. This is Sopris miniature. There's all kinds of interesting states out here. This solid region, which I'll say very little about. One gets to an inner core, which is made primarily of neutrons, protons, and electrons. And the inner core where life begins to get interesting because there's evidence that one is having a continuous transition we'll call a quark-hadron plasma in the deep interior here. For the condensed matter people in the audience, I've indicated what is solid out here. But this is the world's largest dewar, DEWAR. It's full of superfluids, more superfluid than any neutron star will ever be produced in labs on Earth. It has singulus neutrons freely running within the crust out here. Singulus protons, triple P2 protons, neutrons out here. And in the deep interior, it's possible states of pairing of quarks, which are theoretical speculations. There's no direct evidence that they're raise rather interesting theoretical problems. I want to just give just a very brief overview of neutron stars. Some of the physics. They're made primarily in the gravitational collapse of massive stars. The supernova, they're left over. Whereas we've been discovering gravitational radiation, gravitational mergers, and also they give rise to neutron stars behind. The matter, the density in the universe, up to, if you take the density inside a normal atomic nuclei, which is about 10 to the sixth of a particle per cubic Fermi. This one is interesting in densities up to 5 to 10 times that, which is a difficult regime to get to. Why don't they collapse? They don't collapse because the gravitational, because of the degeneracy pressure, in the same way that electrons hold solids up, electrons prevent you from falling into your seat now. Neutrons are held up by neutron degeneracy pressure. In higher densities, the quark degeneracy pressure, which we'll see some interesting experimental evidence for. Neutron stars, since their first discovery in 68, 67, turned out to be central engines in a wide variety of systems. You're listed here, from pulsars that gave binary X-ray sources, repeaters, magnetars, ultraluminous X-ray sources, fast radio bursts, which we don't understand fully, and now, of course, binary neutron star black hole mergers. Theoretically, they're interesting. They're an astrophysical laboratory studying high density matter, studying quantum chromodynamics at high densities, where one can have conditions that are not reproducible anywhere on Earth. Okay. Well, let me give you a very brief history of neutron stars. The neutron was discovered in February. Well, it was discovered in February 32, and then Chadwick wrote a letter to James Chadwick wrote a letter to Niels Bohr announcing his discovery. And this is the original letter, but he writes here, he found this particle which probably has a mass almost equal to that of the proton. Now, from the point of view of energy physicists, particles are very close in mass, good thing. Chadwick, it was a bad thing. And a few years later, after he wrote this letter, he was interviewed by the New York Times, and he said, whether this discovery had any practical importance. I'm afraid neutrons will not be of any use to anyone. So, moralists, do not get quoted in papers saying these things. But that interesting, by September of the same year, he believed that neutron is a new ultimate particle like an electron was challenged by Chadwick. Because he just couldn't believe there could be another particle that's very close in mass to the proton already. The idea of the internal degrees of freedom, nobody thought that in 1932. Shortly after this is February 32, December 33. Altabada and Zwicky proposed making neutron stars, supernova, and they published something in the APS Bulletin in December and a letter in Proceedings National Academy 34. And many people have ever submitted an abstract that's actually published. We don't do this anymore. This is from the Bulletin of the American Physical Society, and it says, we always observe, we advance the view that supernovae represent the transitions from ordinary stars into neutron stars. It's being invented right now, which in their final stages consists of extremely closely packed neutrons. They have the story right. Not only did they have the story right, there's a little clip here from the LA Times in January 19th of 34, where he says, like, the little sphere is 14 miles thick, says Professor Zwicky, Swiss physicist. 14 miles is our best measurement to date. Because we do it in kilometers, but this, yeah. He's quite amazing. And Zwicky, of course, is a person who discovered dark matter as well.
No, the photograph always see a photo.
Yeah, that is a wonderful photo, yes. Well, this has been a very slow field until the past couple of years. Oppenheimer and Volkov, this is the same Oppenheimer, they decided to take the Tolman Oppenheimer Volkov equation for gravitational balance, and this Oppenheimer that's Volkov. They try to make a neutron star made of free neutrons, and very, very, very beautiful calculation where they came out with a total mass of 7/10 of the solar mass. Now we've seen many neutron stars, none of which has a mass that low. Tells us that for interactions that are important here. And nothing very, this field just percolated very slowly. By 1966, Tom Wheeler, wrote up his stance and said in a review with annual reviews, a cool superdense star is fainter than 19th magnitude and therefore hardly likely to be seen. The rapidity of cooling makes detection even more difficult. And that was sort of the situation in late 66. Then a remarkable thing happened. November 67, the first pulsar detection by Jocelyn Bell. You, of course, probably all know the story that Jocelyn Bell, all those beautiful data, and Tony Hewish got the Nobel Prize. This, what a series of justices. Anyway, she was just sitting tracking signals on radio telescopes in Outer Bank in the UK, and she sees here the blank. Something's repeating, and notice it's labeled LGM3. There's LGM1. LGM stood for little green men. And listen, and she remarks, it was highly unlikely there would be two lots of little green men from opposite sides of the universe, both designed to signal at the same time, a rather inconspicuous star of a rather curious frequency. Okay. And shortly after the spring 68, pulsars were identified as rotating neutron stars, both by Tommy Gold, Cornell, and Franco Pacini in Florence here. And sort of began to come together then. Now, at just this point, the first Aspen workshop took place, which was the summer of 69 in Butcher Hall. And everybody recognizes this building is sitting up on the other side of the parking lot, and it's become a part of a big complex now. In 69, the other thing that was here, Stranahan Hall, and Richard, and so that was borrowed from the Aspen Institute to have a workshop. And among it was pulsars and neutron stars. It was a wonderful workshop. On Speta, I was here. The Bloodman, Tommy Gold, Jim Hartle, Peter Goldreich, Chris Pethick, David Pines, Ruderman, and then these three, Al Cameron, they're all astrophysicists, George Field, and Sterling Colgate. This is Sterling, a standard picture of Sterling sitting in under Hot Springs here. Notice I put these three little green men, because they were at the time pushing to have an Aspen program in astronomy, but trying to get support from the NSF astronomy here as well as particle and matter physics here. Okay. Now, let me turn more to neutron stars. There are two approaches over the years, which is one, you study the theory of dense matter, and one, you make up your best guesses, solve the Schrödinger equation. It's a very low, slow, hard slog, because we understand what goes on inside atomic nuclei well. But how do we understand what goes on at much higher densities? There's a tremendous amount of extrapolating there. When we thought in the early days, one of the original ideas here was having one would have quark matter inside neutron stars as well, which I'll come to eventually. But the problem is you can't solve anything. You can write down models. Now, the basic model is quantum chromodynamics, but you can't solve quantum chromodynamics, find a density exactly. There is some people were implementing something called lattice gauge theory, which most of you are familiar with. But the trouble is that finite baryon density, there is something called the sign problem, which precludes being able to do calculations. There's very limited information one can get from laboratory experiments and do nuclear experiments you can't get to very high density. Well, on the other hand, you can do observations. And observations initially were very, very slow. I mean, after the discovery of pulsars, this is the late 60s, many neutron stars were discovered in different aspects, including X-ray binaries, neutron star binaries, glitches, sudden speed-ups, neutron stars. The really big advances have been in the past decade. Now, I want to turn to them. So we're really living now in what golden age of neutron stars. Okay, a wealth of new observational data, even gold. That's what say, yeah. Okay. There have been detections of heavy neutron stars, pulsars. It tells us that the matter that they're made of is very stiff. It's very hard to compress. It doesn't go just like this. You really have to work hard to squeeze it down. Since 2015 and now 2017, gravitational waves, and that in 2015 from neutron star mergers as well. What's very wonderful that's going on there is there's good evidence that the heavy elements, gold, platinum, silver, uranium, strontium, these are all made in binary neutron star collisions. This is LIGO, Virgo. LIGO is the U.S. gravitational wave facility. Virgo is the very Italian radiation. And Kagra is the new Japanese gravitational wave detector, which is going into Kamiokanda. It's in Kamiokanda. It's slowly going online. Yep. In the future, there will be a couple of big machines. Cosmic Explorer in the U.S., Einstein Telescope in Europe, and LISA in space. I want to talk a little bit about pulsar timing arrays, because this is a wonderful subject where it was actually using neutron stars themselves to measure gravitational radiation. I want to talk a little about measuring masses measuring masses and radii of neutron stars directly from the NICER experiment, the box that sits on the space station. I will not say anything about glitches, sudden speed-ups, the implications for stasis superfluidity, and I'm not talking all about cooling of neutron stars, which is an interesting question in itself. Okay. This is just a picture of neutron star masses, and what you see here is masses 0, 1, 2, 3 solar masses. The binary neutron stars, they're all around 2.3 solar masses here. This is the famous Taylor pulsar, the double pulsar, which gave evidence they were emitting gravitational radiation, which Olsen Taylor got the Nobel Prize. There was a remark. I was listening to a talk by a scientific secretary of the Swedish Nobel Foundation. He was in charge of physics. He said, we made a mistake with Jocelyn Bell and Tony Hewish. Here, made sure that Joe Taylor got the Nobel Prize as well. Joe Taylor, of course, was the senior person. Now, of course, it's very hard to measure the mass of a neutron star. You can't look out and weigh it. You have to be in binaries, and then you have to infer from the motion of the binaries, frequencies emitted, what the masses are. I want to point out these three guys down here. These three stars over here have masses almost on the range of 2 solar masses. That's very important. Back to that. I also want to mention that there is if you measure black hole masses in the galaxy, 0.5, they start pretty high. There's a gap, we'll see more of that, between neutron stars and black holes. Okay. Now, how do you go about modeling neutron stars? I'm not going to spend any time in mathematics. The basic idea is you construct an energy as a function of the density, which you construct the pressure. Then you saw the Volkov equation. It shows you how the pressure varies with gravity, G is Newton's gravitational constant, the density. This is the ordinary equation of hydrostatic balance, except for the water c² terms here. Then when you solve for the pressure, you go back and you get the mass by integrating the density. This is rather straightforward industry. If you, for example, take about nuclear physics and create equations of state, pressure versus density and such, and you find results like this. As increasing density, you find, depending upon which you take for the equation of state, families of mass will go up and then come down. And so, for example, this is one of the best old nuclear models. It has a maximum mass of about 2.2. 2.2 is good, just really consistent with data. And over here, it shows the mass versus radius that you get, and these have radii in the order of 10 to 11 solar mass. I mean, it's pretty good.
Limits the mass, the maximum mass. I mean, obviously, you could see the Schwartz radius. I mean, I think it lasts as.
It's a very subtle question, which has nothing to do with these pictures. Yeah. But ask me later. Yeah. Okay. Now, the significance of these stars, what they tell you right away, is they're very heavy. They're heavy means that you must have a very stiff equation of state, otherwise gravity would just collapse it down completely. And if you look at a picture of the mass versus central density I just showed you, comes up, comes down. If you discover a star mass up here, it says all your guesses for equations of state, first equations of state down here must be wrong. I mean, the higher the mass star you measure, more although the equation of state you just throw out the window away. Okay. Now, there's an interesting question though. In quarks, for 2 solar mass stars, and for many years people thought no, and I was responsible for a lot of the bad thinking there, which I hereby apologize. Okay. There are 3 other possible masses for the massive stars. Roger Romani has one. It's about 2.35 plus or minus 0.17. And the problem here is that the neutrons are going rather light, complicated star, 0.03 solar masses here. And there's all kinds of dynamics going on there. It's very hard to pin down exactly the Doppler shifts and stuff. You get enough information to be able to know what the mass is with any accuracy here. Another object over here, which has been around for quite a while, and it's known to have a small light companion, and was awaiting detection by the James Webb Space Telescope of this object to really clarify what's going on. The mass certainly less than 2.5 times the mass of the sun. And there's another one recently announced, which is interesting. It's a pulsar, but it's got a companion that has a mass 2.09.7. A little heavy for a neutron star, too light to be a black hole. But when this one's clarified, it'll be interesting. Something what's going on. Okay. Now let me say just a few words about detection of gravitational radiation. In the summer of 17, there was a spectacular event. I think it's one of the most beautiful events that ever to be seen. Very shortly after the eclipse, it said. This merger of 2 neutron stars were going around each other, merged together. They sent out gravitational wave signals. Gravity wave signals look like this. At the same time, they also knew exactly where it was, and Fermi Gamma Ray Telescope, and these 70 other electromagnetic observatories able to observe it. Well, when it's a complete electromagnetic history of this object, till, unfortunately, sun got in the way and we couldn't get any more data. But this is really an amazing event here. The thing we saw there is in the merger, you probably all seen movies of this, when the stars come together, they finally form this object that we hear that with the big jets coming out. And this thing is kilonova, and it is probably the source of the neutron-rich elements in the universe. It's these objects here. How does that work? Yeah. Here's a very nice picture of the periodic table. Shows you where things came from. And I want to focus on merging neutron stars: palladium, silver, platinum, gold. Ordinary stars burn through. They make the heaviest element you can get ordinary burning in an ordinary star is iron, right? 56. That's very good if you're happy with cast iron frying pans and such. You're in business. But if you're interested in things like wedding rings and all of it, then you and nuclear reactors and all that stuff, you really have to worry they make these other elements. This is when I realized for years there's something called the ARP process. you capture neutrons rapidly on an ordinary nuclei. And people worked out all the sequences and eventually came out with all the elements. The only problem was they had no idea where the R process was taking place. Supernova was sort of a candidate. There were just aren't enough neutrons there generally to explain everything. And so, but two neutron stars merging is fantastic. These are two big bangs of neutrons. They're merging together, and it's an environment that has more neutrons than you could ever imagine. And there's very good evidence of not showing you of making these very heavy elements. There's a lot of work to be done there. I mean, the picture is far from clear, but it looks very likely. The next time anybody asks you you ask somebody where gold comes from, the answer is Costco or something. And you ask where Costco gets it. Oh, they get it in gold mine somewhere. There's a gold mine get that someplace. Where's the Earth get it? And the answer eventually is a binary neutron star merger. Please appreciate every time you look at a piece of gold, the gold atoms in there once in a binary neutron star. It's quite wonderful. Okay. Well, in addition to this spectacular event, there was another event on April 25th, 2019. But unfortunately, it was unlocalized. Only half of the LIGO detectors were working, Livingston, and there were just simply no electromagnetic signals. And we were at a workshop here trying to figure out what it was good for. Everyone was throwing up their hands because there's just no data. Well, there are several other possibilities, which I won't mention here. This is a very nice picture of from Vicky Milagara Northwestern showing this is in the stellar graveyard. These are all the various black holes that are detected by LIGO. These white dots here are neutron stars not detected by LIGO but measured otherwise. There are bars. There are various places where one's beginning to fill out pictures and neutron stars are detected by gravitational radiation. After this morning, there was a notice that present gravitational radiation program is in trouble. Hanford, which is half the LIGO thing, is down for reasons. Virgo's having their own private problems. So the extended lunchtime in Italy. And Congress is yet to get to speed. At the moment, this is we're in the middle of the 04 run, and it'll end sometime late next year. There's not very much data coming in now. Okay. Now, let me talk about pulsar timing race for a few minutes. This is immense fun because neutrons, we've saw neutron stars as pulsars of seeing gravitational radiation. They're now using pulsars themselves to measure gravitational radiation. So the pulsar timing array is, there are several of them now, but this is the nanograv collaboration. Look at 68 millisecond pulsars. These are pulsars that rotate on their axis up to 700 some odd times per second, really fast. And they're very, very stable. And what they're looking at is asking how the frequencies we measure from the Earth are changing as a function of time. Okay. So here, these are showing all the pulsars, 67 here. And we're someplace around here. This is on the scale of the Milky Way. Now, what's interesting is they're looking for nanohertz frequencies. In order to get enough data, you have to wait a long time. So waiting 30 years, so you can calculate easily that the wavelength corresponds to nanohertz gravitational radiation. Here's these 68 pulsars seeing how they're wiggling to get, if they're being affected by gravitational radiation. So the spectrum of gravitational radiation in the universe through frequencies. Now, all the LIGO stuff that makes headlines way down here, these are in 100 to 1,000 hertz frequencies. This is the modulation of the gravitational, the gravitational background, gravitational waves, is on the order of 10 to the minus 22, minus 23.
When the size of the object,
Excuse me?
frequency is set by what? The size of the object.
No, the frequency is set by the time you have to listen to get data. If you have to wait 15 years to get data. You can't be observing microhertz or anything.
About the emitter. Just asking about the emitter. What property?
We'll get the emitters. We'll get there eventually, yeah. And so these are stars way down here, nanohertz, at amplitudes about 10 to the minus 14. Yeah. Okay. What are possible sources, you ask question? Well, one possibility is supermassive black holes in the early universe. These masses of 10 to the 6, 10 to the 10th, but they don't have to be merging. They can simply be rotating about each other, emitting gravitation, emitting radiation. We don't know. I think it's one of the really interesting scientific questions. What is the source of these things? They could be much further back. Could be things coming from cosmic streams. Various things produced in the time of inflation. Well, it's really a tremendous window on the early universe that we've never had before. You must see that. This is showing a pulsar. And what you see in the background is a gravitational wave coming past. And you see the frequency varies. Sometimes it's slow, sometimes it's fast. So you want to observe this for all the 68 and then try to construct a picture out of this. The statistics are very low. Okay. This is put together the following way. It's something called the Helling's down curve, which is a correlation function of the frequency shifts caused by the pulsar. It's divided by the frequencies. It's the order of correlation. Take two pulsars, A over here and B over here. You just correlate the data. And C is the angle between them. So this is C here. What's interesting is you write down this correlation function. And it's rather straightforward to calculate. It's a good homework exercise. And it has this structure. It looks like that. If you do this for electromagnetic radiation, you get a completely different answer. The correlation function just goes to the cosine. So the fact that it has this structure is really a signal you're seeing spin 2, rotation radiation, not simply ordinary radiation. You do sound waves, it's completely flat. Nothing happens. Okay, the data. The data set was released just a year ago, and this is the expected curve. It's not so bad, and things will improve in time. So when it really became see gravitational radiation, this is not the only show in town. There is the South African Meerkat array, which also at the Texas and Shanghai meeting last December, Matthew Bales showed this lovely picture, which is tough to release. But there you see a quite different 77 pulsars, which are mostly different because they're seeing pulsars in the southern hemisphere. They see precisely the same results here. And so it's a wonderful field. Pay attention to it in the future. We're going to learn a lot. Okay. I want to turn to dice here finally. NICER is sort of a refrigerator-sized experiment that was mounted on the space station just 7 years ago in June over here. It's just this marvelous timing of X-rays, measures 300 nanoseconds, good spectroscopy, the range of 10 to 10 keV. And so the object is to try to measure masses in radioactive neutron stars. A marvelous trick. And just to give away the story, 2 neutron stars have been observed, or one has a mass of about 2.7, 1 solar masses. This is the one we know about already. Its radius is about 12.3. And Another 1.44 solar masses, its radius is exactly the same. Think about how that's possible. Well, okay, how does this work? You know that if you have a star, light comes along and gets bent by the star. Or an ordinary light bending, the old Einstein stuff in the textbooks. Yeah. But the star has strong gravity. So that means light that's coming out from the back over here, as it's emitted, can be bent around. So in some sense, you look at a neutron star, you can see the back of its head. You see behind it goes the light bending. Not fully, but somewhat. This picture shows very well. In weak gravity, here's a spot. And the spot goes behind, and it's spots there only half the time. But if you take strong gravity into account, it's shown the more full picture. The spot is really around for much longer. And so you really see evidence of spot for a longer period of time. And so data analysis probably is very, very tough. Here, of course, there's a spot. What is a spot? Neutron stars have spots because they're pulsars. Pulsars emit radiation, emit particles. Particles fall back. It's governed by the magnetic field. So you get a hot spot. You get several hot spots. And people model all kinds of things. And probably a couple of hot spots seems to work. But the picture's not as clean as I say. Okay, so this one begins to learn masses. And so a few years ago, Paul Miller and Lamb, Urbana, found this one object. They came out of the range of 13.7, but as they improved their assumptions, the priors, it came down to 12.3 solar masses. A similar group in Amsterdam, but analysis came out rather similar results up here. You may wonder, how do you deduce a mass and a radius separately? Because all you're measuring is light bending. Light bending at angles, dimensionless. There's going to just be a ratio of mass divided by radius in appropriate units is dimensionless. And the answer is you need to know more. The rotation is very important. The corrections to the signals from the factor of rotations. But there's another parameter in the problem, which is the rotational frequency. There are many more as well. I'm not going to get any details, but it works. Okay. From this, what do we learn? Okay. One thing we learn is the equation is stated it's rather stiff. The lovely picture of Sanjay Reddy showing possibilities of mass versus radius, and people be conjecturing there might be very squishy neutron stars over here, but everything seems to be falling in here. Okay. Soft equations are stated to be excluded, and also large first-order phase transitions in the matter are also excluded by this data. What do we do with all this? Okay. So it's the basic message is from nicer. First, I mentioned these two stars have the same mass, have the same radius. And the first thing you expect is that as you make things heavier, they get pulled in further. If you have a very small head, you lie it on your pillow at night, it doesn't dent very much. You really sink into it, it dents a lot. How do you make a pillow, no matter how heavy the head that falls on it, goes down just the same amount? You might see by nucleons, just by describing neutron stars in terms of neutrons and protons, which has been the canonical way of doing things for a gazillion years. The small is a radius. Let's keep moving this way. Nucleons cannot explain this behavior. There must be some other source of pressure inside the systems going on. My old postdoctoral Kojo, who's now at AEK, with a very, very simple explanation. Just take a piece of matter. It's made of neutrons and protons. Inside the neutrons and protons are quarks. And think of the distribution of quarks and momentum. What momentum states do they occupy? Well, if this was very dilute, you would say the number of quarks versus momentum will look something like this. And it's uninteresting. Imagine you start to squeeze the system, the number of quarks per unit volume starts to go up. So eventually, the number of quarks each state eventually rises to 1. It's just the Pauli principle. You go to higher density, what happens, where the further quarks go, they have to go to higher momenta. But here, what you're seeing here is a very simple explanation how when you squeeze matter, the Pauli principle is simply pushing the quarks to higher momenta. These quarks at higher momenta must be with a lot of energy. They're producing pressure. So what I believe is it was really beginning to see evidence of the onset of quark degrees of freedom from the simple data point that the radii need to remain constant with higher. Okay. This is not to say that when it's gotten quark matter. I'm not simply saying that the neutrons and protons have dissolved into a sea of quarks that is degenerate, and because this is an event that will happen still while the quarks are bound inside ordinary nuclei. They squeeze them together, they get harder and harder to compress because of the internal quark structure. Yeah. But what can we do with this? I just want to spend a few minutes.
And help if you attack the question. It's shorter and more.
We'll find it. Good. Thanks. Okay. I just want to comment about quarks and dense matter. Quarks everywhere. I mean, it's one of the wonderful seminars here was in Hilbert Hall, Murray Gell-Mann explaining QCD and quarks. Hilbert Hall is now replaced by Hilbert Space with the universe before a microsecond filled with hot quark glued plasma. Ultraviolet heavy ion collisions, like a relativistic heavy ion collider at Brookhaven, you squeeze, or at CERN, you collide a big atomic nuclei, you may know it's a quark matter. Yeah. And they certainly should, one expects to begin to occur inside neutron stars. Okay. Let me see that. I want to come on to this. One comment about matter in general. I showed you this picture of the equation what you get from nuclear matter. And these make nice families of neutron stars. But this has been replaced now by what's called chiral effective field theory, where you don't try to find potentials, do an expansion and increasing in momentum of particles in nuclear matter. Some heaps of diagrams. You get sort of energy per particle versus baryon density. This is nuclear matter. You see, as you went on, you start to get large error bars here. It covers you in the range of the nuclei, but it doesn't get you very far beyond 1.5 to nuclear matter density. Now, there are really very fundamental limitations when you think of equations of state. If you base them on just nucleon-nucleon interactions, first thing, in the neighborhood of ordinary atomic nuclei, it's fine. But when you have higher densities, several problems occur. One simple dead problem, of course, is that sound speed begins the speed of light. And while nobody's ever proved that the thermodynamic sound speed be less than the speed of light, if it is as a mathematical exercise, it is still. Mr. Einstein would complain tremendously. It's such a word the case. So that's no good. And people invoke two-body forces, but there are three-body forces, four-body force, but it doesn't end. And it goes with N. And chiral effective theory, which was better than this, begins to break down. Then you ask the question, can you really describe the forces inside dense matter in terms of static few-body potentials? And can you even describe the system in terms of standard laboratory particles, asymptotic particles, neutrons, protons? Things get very dense. Another way to ask the question is, you're an atomic physicist, and you do niobium scattering, like nuclear scattering. You know everything. You know everything what niobium does on niobium. Would you predict that solid niobium was a superconductor? And people think yes. The other degrees of freedom are coming in because it's a much more complex, rich problem. And there are further degrees of freedom. I mean, as you all know, if you ever play with eggs, you could do egg scattering, you know, everything there is to know about eggs at egg density. Then if you want to go up an order of magnitude, you have this funny yellow soup you have to worry about, which involves completely different degrees of freedom. Okay. So, equations say based on nuclear interaction alone, you have nice looking models. The input physics is wrong. So long degrees of freedom at higher densities over here. And the fact that it seems to work, not make it right. We'll illustrate with a simple mathematical theory. Theory is canceling sixes. I mean, 16 over 64 is great. I mean, 19 over 95, and even 18 over 85. It's close to a fifth. It's got to be right. And it's the same situation in neutron stars. People say, we'll give you an answer and say, look at my beautiful neutron stars. And you twitch your answer, you're just canceling the sixes. Okay. How do we construct the equation? You say, I'll just spend 2 or 3 minutes. But this work that I did with Toru Kojo, Tetsuo Matsuda, published 2 years ago. You know the equation states low density sort of and high density sort of. It's the in-between regime that's very hard. And I don't want you simply just say, well, those nuclear physicists, they have a hard problem. I want you to think about how to go about this. Because what I'm discerning is pressure versus chemical potential. It's a nice thermodynamic variables for doing a problem. But at low densities, one is nuclear matter. You have some equation. High density of quark matter, and what's going on in between? It's really the problem of if you take atomic sodium gas and you begin to squeeze sodium gas, eventually you'll end up with a sodium plant with lots of sodium atoms and electrons. How do you go from one set of degrees of freedom to the other? You're changing from nucleons to quarks, which are more complicated because you see deconfinement. It's a very difficult problem, which we would really welcome simple models that can span this regime. But anyhow, see down here you have nuclear, here you have quark. We're just trying to make a model that could fit in between. It turns out it's a very highly constrained exercise, not much choice. So we approach just parameters. They have foundations, but I just want to say what they are. We assume that there's short pulsion contact interaction, like in atomic physics, contact repulsion, strength GV, and there is a pairing interaction, just plain BCS pairing, called H. Okay. As I go on, simplest model is no interactions, and you picture looks like the nuclei down here, quarks over it. So this is a very soft equation of state, and you can't get to you can't get to 2 solar mass neutron stars. You see, you need interactions, repulsion. Repulsion does what? Repulsion pushes the equation state out this way, softens it. Now, there is the thing wiggles. But here, pressure versus chemical potential, you're not allowed to have an inflection point. Just elementary thermodynamics. Hold on. There's an inflection point over here. That's bad. Okay. In fact, we're instructed that we don't allow that. Okay. Oh, what do? Now you worry about pairing, BCS pairing. BCS pairing pushes the whole thing back this way and gives you a nice consistent picture. That's what we've been doing. Just between a simple repulsion, get the higher masses, and BCS pairing give you a consistent equation of state. This is very nice. This, you can't tell from the numbers, this is indicating really strong two-body correlations. We love two-body correlations because what you know is that if you take quarks, gas of quarks, and you lower the density, they want to come together to form nucleons. we want to form very strong three-body correlations. And so here's really evidence over here that to understand neutron stars, you need initially some strong two-body correlations over here. The picture, how you get down to nuclear densities not worked out. Only nice interpolations.
Conducting quark.
This the superconducting, the strange. Everybody's in ratings in here. Okay, I won't show this. I'm going to come to the end. What's interesting about this is that if you plot the sound velocity of matter versus density, there appears to be a bump in the sound velocity over here. This is something not seen in any nuclear matter theory whatsoever. And finally, if we come back and compare masses versus radius, this green box over here is basically the range of error bars, or the confidence region that one saw that's consistent with nicer experiments. You just sail right up the middle here. It sounds like a very, very consistent picture here. Down here, ordinary nuclear matter doesn't do the job over here. Getting rather good evidence for this rapid pressure rise from the onset of quarks. Okay, so let me summarize here. The nicer experiments are really critical. It's shown two things. One, the chiral effective theory of matter produces a much stiffer equation of state, allowing us to have close to 30-kilometer neutron stars. It also produces puzzle the radii of these stars. What we need, of course, is many further measurements. There are several in the pipeline here. But within the next year or so, the picture will begin to fill out more. Now, finally, I just want to mention some challenges for the future. What we need to understand the internal workings of neutron stars is to build a phenomenological picture that's consistent above nuclear matter density using both gravitational radiation and nicer data. I did not mention when gravity wave systems come back on, you'll be getting up to 100 neutron star mergers per year. It's going to be a fantastic data source. I also want to stress one has to develop microscopic pictures of how one changes the gradient of freedom from nucleons to quarks. People are very good at drawing curves. They say, here's the pressure, P versus rho. That's just a curve on paper. It's not a microscopic theory. It's not good enough. They all do curves. How do you understand the physics, microphysics, at the level of QCD? We can't answer what are the lightest and heaviest neutron stars yet, or what are the lightest black holes. And so eventually the future NICA data, plus the gravitational data, will really begin to fill this picture to a tremendous extent. So stay tuned. It's a lot has been happening. And if there's only one take-home message, every time you look at a piece of gold, remember, think neutron stars. Thank you.
Yeah, thank you very much for the. I was wondering if you can comment a little bit more on the rotations and for.
Good luck.
I was wondering if you can comment a little bit more on the implications of rotation for equation of state or for the maximum neutron stars, and if you're rotating your mesh.
That's a good question. The answer is the rotation rates are. Thank you. Can I comment on effective rotation on effective rotation on equation of state and such? The answer is not very much. The rotation of neutron stars on the scale of the internal energies, not very. The rotation energies on the scale of other energies are not very large. Let's see.
Just the same question, but for magnetic field.
At lower densities, the same question except for magnetic fields. At lower densities, magnetic field energies can be big. I mean, get up to 10 to the 16th, the 15th Gauss. And those energies can be very large. After a while, it's like the electron degeneracy pressure rising rapidly. And within tens of meters into the star, magnetic fields are not doing very much. Except when you stay put, because the electrical conductivity is very high. It's hard to move flux in very high unconducting environments. There.
Chandrasekhar limit is 1.4 solar masses. You've got these neutron stars at 2 solar masses.
Very wonder. I didn't plant the question, but it's a good one. Everybody, the Chandrasekhar limit is 1.4 solar masses. How come I have 2 solar mass stars here? Because Chandrasekhar has nothing to do with this problem. Chandrasekhar mass tells you if you have these stars supported by electron degeneracy pressure, that 1.4 is the maximum you can get to. Beyond that, but here, stars are supported by neutron degeneracy pressure and eventually quark degeneracy pressure. Plus all the complicated interactions that are just Coulomb interactions. There's been a lot of confusion. Binary neutron stars will appear to be 1.3, 1.4 solar masses. Figure that the problem is solved. They're all going to be avoided the Chandrasekhar mess. Why worry? It is completely wrong. Let me take this. Okay, Jimmy. 1, 2. Yeah.
You mentioned the superconductivity. Have any consequences in light of the outgoing observations?
Not in light of. Thank you. I'm a slow learner. I mentioned superconductivity. Does that have any implications in light of the ongoing observations? Not of the ones I talked about. Raise this question: speed-ups of neutron stars, where what you see are neutron stars percolating on, and suddenly you go faster by one part in 10 to the 6, say, and then slowly relaxes back. Now the question: how do you make a machine that can relax back over a month's time scale? It has a really it's a very well-oiled parts inside in these superconductors. I mean, there's a good question back.
How do we know that there is a solid shell?
And
How do we know that there is a solid shell?
there's a shell.
And if we do, what are the other solid state properties that we know? Is it lattice or?
How do we know there's a crust? Because if you look at the pulsar timing, it's very accurate. I mean, it's much better than good Swiss or Japanese watches. But it's up there with atomic clocks. What it means is the magnetic fields are producing all the pulses that we see, but they don't wiggle around inside the star. They much more noise. They're very firmly anchored. So the existence of really good pulsar timing, very strong evidence for the crust. Yeah. There are a lot of interesting physics in the crust.
Is solid all the way through?
To the center?
Yeah.
No. If the crust is maybe a kilometer thick or so.
How do we know this?
That was part one. Where I said there are 2 ways of looking at things. Think about it and look. That's physically. Eventually, that's a very interesting question. When you come to you squeeze matter, you've asked this question when you squeeze far enough, does it want to stay liquid or does it want to stay solid? Or does it become a liquid? Now, those you can do. It basically solid state calculations, solid state simulations. And see, you form liquids, yeah. And you have liquids, it's not surprising. You have liquid helium-3, light things like to be liquids, like nuclei, like to form liquids, not solids. Yeah. Sure. Did you want
I think we've got a couple minutes.
okay, sure.
Question one, maybe that's even.
Mine is probably not so much a question, but a comment. I'm thinking about your puzzle about crossover from European degrees of freedom to quark degree of freedom. I cannot resist pointing out that there is similar crossover known in soft matter physics. Naively, it feels very similar, but hierarchically organized together was the solar from the situation when bigger blocks versus smaller blocks contribute to observe the equation of state. So you may want to look at.
I'm going to challenge to repeat it, that in soft matter physics, one has similar situation where you can get crossover, matter dominated by bigger blobs, matter dominated by smaller blobs. Have to learn, yeah.
When you mentioned the temperature of the neutron star, temperature,
Yes,
in which frame of reference is this temperature quoted? Because that can vary strongly because of the Lorentz transformation of temperature.
no, sure. That's the old OP problem. You always define temperatures in the local Lorentz frame, local really forming Lorentz frame.
Measure the temperature.
How do we measure? We cannot measure the deep interior. We don't have, I mean, the thermal pen is good for measuring inside steaks. We don't have thermal pens for neutron stars yet. What can we measure? We can measure radiation coming out from a neutron star. And say you point your telescopes up and you see a blob in the sky, and you see something roughly like a black body spectrum. Then how do you go from that for a temperature? Well, it's hard because the outside of the neutron star is this big magnetosphere. It's a complicated business. But you don't know, are you measuring surface temperature? Are you measuring further out? Are you measuring a hotspot on a neutron star? None of this is very clear. You really need good modeling for this and good data. And we don't have it yet, adequate data.
All right, I have just one more question, and then we'll.
Oh, wonderful talk.
Thank you.
What about the dynamical transition from a neutron star into a black hole? For example, when they collide and go over the critical mass.
Yeah. What was the question?
Question is, what is known about the dynamical transition from a neutron star to a black hole? For example, when they collide and go over the critical mass.
Give me multiple choice, I could answer that. Yeah. What is known about the transition from a neutron star to a black hole? For example, one can think seriously, the binary neutron star merger, the beautiful event from August 17 left a blob of around 2.7 solar masses, hot and rotating rapidly. As it cools down, it's not going to. I don't think we have neutron stars of 2.7, about 2.35. I think it's about the highest one I can get. So as it cools down, it will eventually go form a black hole. How that happens is, I can't write down a simple general relativistic calculation, but there are certainly things that are happening now. Yeah.
No evidence yet that it did form a black hole. Is there?
Who's taken?
Is there any evidence that it did form a black hole already?
No. You'll know. Listen.
Well, on that note, thank you very much.
Anyway, okay.